Hi. Let's hear one example of statistical sampling. For this example, we use some arbitrary probability density, some function that is easy to integrate just to understand what's the process. This is not a usual distribution, although it may happen in some cases. It's a parabola. And we have this expression for this probability density. And we see that it has two roots at 0 and at x0 equal to b divided by a, where a and b are the parameters here that describe this family of parabolas. And we have the cumulant, which is the integration from 0 to y, with y being any value, any real value. We start from 0, but we could start from minus infinity if we define that the probability density is 0 outside the range between 0 and x0. Okay, so it's 0 in this side, everywhere, and different from 0 just in this range. Then we can integrate from minus infinity to y. And you will remember the integration of the Gaussian that we used in the first class. It's the same thing, so this is the cumulant. And it's easy to integrate. We integrate the cumulant from 0 to y, or from minus infinity to y, and we get this result. Of course, this result, and we can substitute the value y equal to x0 or equal to b divided by a, and we get this value. This is the equal to the integration of the cumulant from minus infinity to plus infinity. Okay, it's equivalent to that integration. So over the entire range of possible outcomes of any event in this statistical system. And usually we want to normalize it. We want to say that the integration of the probability over any possible outcome is equal to 1. And then we have this condition to be fulfilled. So we can select the parameter A and B that satisfy this equation. And of course, the derivative will be 0 at 2 points, y equals 0, y equals b over a, and corresponds to these values because the probability density is the derivative respect to y of the cumulant. Okay, so the cumulant will be something like this, some function like this. Of course, we can add or subtract a constant in the cumulant. It will not change the underlying probability distribution. And what we see is that the cumulant is monotonically increasing in this range. It starts from 0 here, if we choose an appropriate constant, and increases up to 1 without ever decreasing. So it's a monotonically increasing function in this range. What the statistical sampling theory says is that we can use this function, the function p of y, or the cumulant function, to sort events, any number of events, according to the underlying probability density, that is px. So what the statistical sampling says is that we can sort using the cumulant function a distribution of events whose probability density will be equal to this one. They will have a peak at the same point, and will be 0 here, and 0 everywhere else. Okay, so let's see how to do it in practice. Let's see how to do it in practice. The idea is the following. We have this, I have plotted this, the cumulant here, the cumulant, just in the region where we want to sort the distribution, okay? Because it's 0 from below 0, and it is 0 also above B over A. So we don't need to sort in this region. We restrict the events to values of Y from 0 to B over A. And the 0, this range exactly corresponds to the range 0x0 here for the distribution, the probability distribution. Okay, so we have this plot of the cumulant. Now, suppose that we divide this x of py into a number of bins with delta p. Okay, so they are narrow bins along this axis, all with the same width. And also here in the y x, we divide with bins with delta y. They don't need to be the same. In fact, they cannot be the same width. In fact, we have to choose delta y much larger than delta p. Now let's look at the following. Every bin in the xy has width delta y, and they determine range delta p with capital delta in the vertical x, in the x of the cumulant function. So we have this large range delta p determined by the width of the bin delta y. And of course, the function is important to describe it, how the range delta p depends on the width delta y. Okay, we will assume here that we can do the range delta y as small as we want, but this relation will be always valid. Okay, if we decrease the width delta y, we have to decrease proportionally delta p in order to get this inequality satisfied. So let's suppose now we can somehow have a uniform distribution here. So I can select events along this axis. Let's observe that when I have this delta p defined, I can count how many intervals, how many bins small delta p will appear, will be inside this range. Okay, and the width delta p is given by p prime over y times delta y if we make delta y sufficiently small. So we linearize the function in this region, and we can calculate delta p, the range delta p. Okay, so what is the number of bins delta p that will appear here? It's just the capital delta P divided by the small delta P. So this is the number of events. So the number of beans that I have here will be equal to delta P over delta P, capital delta P divided by small delta P, and equals to P prime Y delta Y, right? So we can calculate the number of beans multiplying this function by dividing this number by delta P. So we have the number of beans equal to P prime at the point Y multiplied by delta Y divided by small delta P. This is the number of beans that we will have here. Suppose that we can sort a number of events uniformly here. So uniformly means that the probability of any event to fall in any of these beans is equal, okay? A constant probability here. So if I have a large number of events sorted, the number of events in each bean tends to be the same. So the number of beans tends to be the same. It means that the number of events inside this range delta P, which corresponds to delta Y, okay, the number of events that falls here in this range, which includes some number of beans with delta P, they are the number of events corresponding to the range delta Y here. Okay, so we have this range delta Y, and for each event here in this range, I associate a value Y. So sorting the bean here is equivalent to sorting the value of Y. And I make this correspondence. For each bean, I associate a value of Y in this range. So when I have a number of events in this bean, I have also a number of values of Y, of the corresponding value of Y, sorted in my distribution, and associate the number of events here in this bean to the number of Y I have here. So just collect these numbers, and I have the number of events that I have Y. So for any event that falls in this range, I have Y in this range. Of course, usually we don't sort inside the bean. We have the central value of the bean as the value for which we attribute all these events. So any event that fall here, you have a single value Y associated to it. And when we make delta Y sufficiently small, it will correspond to a good description of the probability density. So the number of events will be proportional to P prime, the derivative of the cumulant with respect to Y, times a constant, because we have delta Y divided by delta P is constant. Okay, both are constant. So the number of events will be proportional to the derivative of the cumulative distribution. But the cumulative distribution is exactly P of Y, where this small p is the probability density. So the number of events, or the frequency of events that is sorted there, is equal or proportional to the probability density. So the number of events in that bin corresponding to this range, okay, will follow a distribution equal to our sampling distribution here. So this is the main aspect of this statistical sampling. We have the cumulative distribution and sorting uniformly events in this range, and choosing, using this cumulant, choosing the value of y, we end up with a collection, a set of values of y, which are distributed according to this distribution. And why it happens? Because if we pick different bins here, they will be always proportional to the derivative. So if we sort this bin, for instance, the derivative is small, so the range delta p corresponding to this bin will be smaller, and the number of events that will fall in this range and therefore following the corresponding range y for y will be smaller than here. So everything will be proportional to the derivative of this function, and therefore proportional to the probability density. So this is the theory corresponding to statistical sampling. And as you see, the important fact is to sort uniformly this distribution. So this is also challenging in all practical applications, and is an important aspect of the Monte Carlo method, is to learn how to sort uniformly distributions or quasi-uniformly distributions. So probably you have a lot of questions about this theory. So one may be, what is a uniform distribution? So uniform distribution is a constant distribution in some range. Of course, you want to normalize it some way, so this constant must be equal 1 over b minus a in this range. So this is a uniform distribution. Usually we want to sort the numbers between 0 and 1 because our probabilities are usually normalized to 1. And so kappa must be equal to 1. This is a uniformly distribution, which is also called the random distribution. Why do we need the bins of width delta p? This is an interesting point. Notice that in fact, I could just define bins here and the corresponding range here. Then I sort values between 0 and 1, which corresponds to the maximum here in the integrand, if the cumulant is normalized. And I just count how many numbers are inside this range. Yeah. But the problem is the numbers here are real numbers between 0 and 1. And the question is, how do I choose a real number? Can you understand how you choose a real number? Let's say you want, I want to choose p over 4. How do I get this number? P is a irrational number, so we don't, it has an infinite number of digits, and I will never know what is the number. So at some point I have to cut this number and say, well, I will pick this number as representing pi, and someone could round in the next digit and would pick a different number for pi, very close to mine, but with one more digit. So what we do, in fact, is to pick a set of numbers as a real number. So in practice, we use the real numbers as sets. And we define the real number inside some range, which corresponds to the place where we cut, how many digits after 0 we want to keep. So this will define the range delta p. So this delta p is in fact important in our statistical sampling theory and in the Monte Carlo method, because it will tell us how large can be, must be delta y. I must keep this relation valid. So if I choose real numbers up to the, let's say, 5 digits, delta y cannot be a number with 5 digits. It must be much larger. Okay, I have to cut it much before, let's say 3 digits after 0. So this is why I introduced delta p here, to remember that when we are talking about real number, we are talking about sets of numbers. And the width of the set that we are choosing will limit somehow the precision that we will have in delta y, and therefore in the reproduction of the distribution probability. Okay, so this is one important point. People who are interested in this can look for Borel sets to understand how real numbers are connected to sets. So Borel sets is a way to define real numbers somehow. So look at the web. This is not the main point of our course, but it's useful to have at least a superficial knowledge about it. So what happens if delta p is not small? I just said it will limit the distribution. Let's see here. We divide the y-axis into beams of equal width. The relation is this, indicating that beam width delta p will be different for different values of py. So can you imagine a situation where it would be more useful to choose delta p instead, delta p constant instead of delta y constant? So we choose delta p constant and delta y will be variable. So let's see our figure again. We have here delta y that we decide that are constant, and due to this curve that is not a line, it's not a straight line, delta p will vary depending on the position I place my beam. So delta p will be variable and that delta y will be constant. Can you imagine some situation where delta p should be constant and delta y variable? You will see that there are some cases, very interesting cases, and important, where we will choose in a different way this combination. So delta y may be variable and delta p may be constant, or even both can be variable. So this is associated to reduction of variance reduction technique, and this is a topic of discourse. So this is the central part of our course, and I have here some exercises as extra class activity. So try to generate a set of random numbers and use this set to obtain events distributed according to our probability density. So you have to apply the statistical sampling to our cumulant and obtain a set of events distributed according to this distribution. Okay. Here we fix the parameters somehow and remember to normalize the distribution. Some hints how to generate a random number. There are many ways. You can throw dice, use a roulette, or ask your friends to say numbers from 0 to 100, for instance. This is the range you choose here is related with delta P that we just discussed. Because if you we want random numbers from 0 to 1. If you say to your friends, tell me a number from 0 to 100, you have to divide it by 100. And it means that the numbers that you get are distant from the closest number by 1/10. If you ask your friends to say numbers from 0 to 1,000 and divide them by 1,000, your precision will be 1,000, and the result that you get in your the reconstruction of the probability density will be much better. Okay, but for this problem, I think that from 0 to 100 is enough. There are other ways to choose to sort random numbers, and this is a question. How can you use the chronometer of your smartphone to obtain uniform distribution? This is very interesting. This is a method of random number generators. And as you see, there are some softwares that give you a quasi-random number distribution. So there are methods to use computer to generate random numbers. Usually real random numbers, not quasi-random numbers as we get in a computer. They are sorted by using some natural uncertainty, and the chronometer can give you this natural uncertainty. Okay, so this is what I have for today. This is the second class of our course. And what we have seen here is the basic of the statistical sampling, which is the mathematical theory that gives the rigorous concepts behind the Monte Carlo method. So the approach here was quite informal. It is not rigorous, but in the bibliography you can find more mathematical and rigorous description of the method of statistical sampling. So take the books in the bibliography and read the chapters related to statistical sampling. See you in the next class.